Bloodhound SOC, you're cleared. Engine start. Bloodhound engine start. Ready to roll.
This is Bloodhound SSC, or supersonic car. It's planning to find its way into the record books by becoming the first car to break the 1,000 mile-per-hour barrier. This is Wing Commander Andy Green, the man who'll be driving the car. A former RAF fighter pilot, Andy already holds the land speed record by becoming the first man on Earth to break the sound barrier driving this car, Thrust SSC, in 1997. In this programme, we'll be finding out just what sort of physics problems Bloodhound engineers are having to face to break the 1,000 mile-an-hour barrier. From managing the forces on the pilot and the car to modelling complex aerodynamics, designing rocket propulsion systems to literally reinventing the wheel. The Farnborough Airshow 2010, and the first time a full-size model of the Bloodhound car is unveiled to the public.
This is the Bloodhound supersonic car, the world's first 1,000 mile-an-hour car. Its performance will take it from stationary to being 10 miles away in 100 seconds. This is the cockpit, this is my office, this is where I'm going to exercise my skills as a jet fighter pilot to control this car, to run the jet engine, the rockets, and to keep it straight while it accelerates at 2.5 G, decelerates at 3.5 G. The J3434001 Typhoon engine is going to create 9 tons of thrust in full reheat, and added to that we then have 12 tons of thrust from the Falcon rocket, giving us a total equivalent of 135,000 horsepower. That is the equivalent of 180 Formula One cars, and that is how the car will go from 0 to 1,000 miles an hour in 42 seconds.
Summer 2010, and Bloodhound engineer Annie Beresford has come to White Waltham Aerodrome in Berkshire to meet Andy for the flight of her life. She's agreed for Andy to take her up in his private plane to feel firsthand the forces, often called G-forces, that will be pummeling Andy's body and organs when he drives the Bloodhound car. G-force is a way of predicting the effects on our bodies when they're accelerated by relating the forces they feel to the effects of gravity. The reference point is what our muscles have to do to support our normal weight when we're standing on the ground. This is 1 G. Imagine we cranked gravity up to twice its normal value, an effect that can be simulated on a fairground ride. Everything would feel twice as heavy. This would be like 2G. At 3G, everything would be 3 times as heavy, and it would start getting hard for your heart and circulation system to keep forcing enough blood up to your brain to stop you from fainting. Andy feels similar forces when he accelerates in the Bloodhound car, and he can practice overcoming the effects in his aeroplane.
Flying this aeroplane is very useful in terms of simulating the G profile that I'm going to experience in Bloodhound. Now, because I'm accelerating in Bloodhound, I'm sort of lying back, I've got my feet out in front of me, so it's driving the blood from my feet to my head. It's like hanging upside down, or in aeroplane terms, negative G.
When the rocket fires, he'll feel just over 2G. It will feel like he's hanging upside down with twice his normal weight. The sensation is of everything being pulled backwards towards the top of his body, and his blood will collect in his head.
During that period, of course, the body adapts. It starts to cope with all of the blood trying to force itself into the head. It reduces the blood pressure, dilates the blood vessels, trying to adapt to this really uncomfortable situation.
When the car decelerates, he'll feel 3G in the other direction. Everything will feel like it's being pulled towards his feet, including his blood.
That is the bit where I need to tense my legs, tense my stomach, stop the blood rushing away from my head. Otherwise, quite simply, if you relax at that point, you will pass out. I cannot imagine being able to do that without fast jet background, so I'm very lucky to have that.
Rebel.
When a plane turns a corner, G-forces act sideways.
Right, first thing I'm going to do is just flip it upside down. Ready? Okay, upside down we go. And that's minus 1G. Okay, it's not desperately comfortable, but it's not too bad. How's that feel?
That feels fantastic.
Good. Just hold tight for a second. I'm going to put the stick fully to the left and we're going to roll through 360 degrees. Okay, 3, 2, 1, now. Wow! I won't do that again. Right, what I'm going to do now is just give you experience a little bit of positive G. Okay, that's coming up to about 2 positive G. If you actually try and pick your hands up now, you'll start to feel, they're actually starting to feel quite heavy. If we come up to 3G, a little bit more. Now just try and pick your hands up again. Start to feel how much heavier they are. It's getting quite hard work now, isn't it?
I think the thing that struck me most about travelling at what would be high speed for Bloodhound was the difference from the acceleration to the deceleration. So the fact that you get the negative G followed so quickly by the positive G, and your whole body just reacts so differently. It's, you know, it's really easy to think, oh, it's like somebody pressing down on you, but actually your eyesight starts going, your arms feel so heavy, you really can't feel them very well. And actually trying to concentrate and stay breathing, as well as what Andy's going to be doing with everything else, the steering wheel, the brakes, he's keeping it in a straight line. It's incredible to think he's going to be actually going through that.
Okay, how are you feeling so far?
Feel okay?
Good, right. We'll just try a little bit of sustained G and I'll just do a loop. That's about 3G there, and we'll just keep pitching up. See the speed fleets off as we go over the top. Even this aeroplane can't hold the power all the time, or speed all the time. Then coming back out the bottom, you can feel the G come on the bottom back to 3G. You feel that little bump on the way down? That's our wake turbulence on the way up. That's the sign that I flew a perfectly square loop. I'm only pointing that out because it doesn't happen very often.
I've got a huge amount of respect for what Andy does. It's very easy to you know, listen to the numbers of negative 2.5G and positive 3G and think, oh, okay, you know, that doesn't sound that crazy. But actually, when you experience it and feel how difficult it is to function under those conditions, it makes you realise what a tough job he really is doing out in that car.
In the Nevada Desert Testing Center, work is going on to test a special hybrid rocket that will help get the car to 1,000 miles an hour in just 42 seconds.
This is a 6-inch rocket. This will deliver around about 9,000 pounds of thrust. The full-size rocket is 18-inch diameter, 14 foot long. That'll give us 27,000 pounds of thrust. And that will help us to get to 1,000 miles an hour in 42 seconds. It takes about a quarter of a second for the fuel grain to start and then the thrust to begin. The entire runtime of the rocket is about 20 seconds.
In a rocket, the burning fuel expands and pushes backwards on the exhaust gases and forwards on the rocket motor. This is an example of Newton's third law, an interaction that pushes the car forwards and the exhaust gases backwards. The faster you can burn the fuel, the bigger the force that accelerates the car. But the rocket engine isn't the only power on board. Before the rocket fires, this Eurofighter engine will need to get the car up to 300 miles per hour and, crucially, allow Andy to control the velocity of the car once the rocket fires. In a jet engine, fuel is burnt using oxygen from the air. A fan is used to draw air into the engine, where it's compressed to increase the pressure. As the fuel burns, exhaust gases are ejected at high pressure and the car is propelled forward.
So what we have here is an EJ200, which is one of the Eurofighter Typhoon engines. It helps get to 1,000 miles an hour. Jet engine looks fantastically complex, but in fact very, very simple. Suck, squeeze, bang, blow. So what we see at the front here, we have a fan that sucks the air into the engine. Come along to the next stage, we have the compressor. That compresses the air 26 times. We then put fuel in. These are the fuel lines. That injects into the hot gas, that ignites, that's the bang. The exhaust from that rushes past the turbines, they rotate and they spin the fan at the front. What's left over, the exhaust gas rushes out the back. That results in us having 22,000 pounds of thrust, and that allows us to get to 1,000 miles an hour.
It's one thing getting the car to 1,000 miles per hour, but it's another thing being able to steer it in a straight line. One of the biggest problems is that the faster a wheel is spinning, the harder it is to turn sideways. We call this the gyroscope effect. When wheels are spinning at 10,000 revolutions a minute, it has a massive effect on steering, and that's a problem if you need to correct for the wind or a bump on the ground.
What we've got here is a replica of the wheel of the car. These wheels are going to weigh about 100 kilos each, and during the running of the car, they'll be travelling at about 10,000 RPM. Forces on the rim of this wheel are about 50,000 G. What we've got here is a device to demonstrate the gyroscopic forces when we're trying to steer the wheels of the car. So if I get Mark in to give me a hand, if you'd like to hold onto that, just try and turn that like a bicycle wheel. It's quite easy to turn.
It's very, very easy to turn there.
So what I'm going to do is I'm going to spin this up quickly, and we're going to do the same thing and see what happens. Give it a go.
It's a lot harder.
See the wobble on that? So imagine this wheel is one of these, so it weighs 100 kilos and travelling at 10,000 RPM. That's the sort of forces we've got to deal with when we design the steering of this car.
To overcome this, the team have had to put in Bloodhound's version of the power-assisted steering you find in a normal car. It's a powerful hydraulic power steering system without which Andy wouldn't be able to turn the wheels. It's important because even a tiny side wind could blow the car hundreds of metres off course. The wheels have to be exceptionally strong to stop the rims flying off because they're going so fast. Imagine spinning a jelly around on a turntable. It wouldn't be strong enough to hold its outer edges in orbit, so bits of jelly would fly off. At the speeds that these wheels are spinning, normal steel would behave like the jelly. It would be ripped apart. So the wheels will need to be made of very strong material. Finding a jet engine and a rocket that will get the car up to 1,000 miles per hour isn't the only challenge. They need to design a shape that'll allow the car to cut through the air and stay on the ground at that speed. That's why the Bloodhound team brought in help from the University of Swansea to work on the aerodynamics of the vehicle. There are two forces Bloodhound engineers have to watch out for. The force of lift, created by the pressure of the air pushing the car upwards, and the force of drag, created by the air pushing back on the car when it moves forward.
From the perspective of an aerodynamicist, the main challenges are, I guess, some of the obvious ones. Can we keep this car on the ground at 1,000 miles per hour? A vehicle like this wants to take off. And we've got to make sure it doesn't take off. Also, we've got to try and minimise the drag that's acting on the vehicle. If we can reduce the drag that the air is causing on the vehicle, then we've got a better chance of getting to 1,000 miles per hour with our rocket and our jet engine. When we're talking about the drag that's acting on the Bloodhound supersonic car, we could think about that force as the force that you would experience if you were to wind down the window on your home car just going down the road, put your hand out. The force that you would feel on your hand, trying to push your hand back, is a drag force. So we're aware that air can exert forces on objects. It can exert a force on your hand, or if you're cycling along, you can sometimes feel the force of the air pushing you, trying to push you back. That's a drag force.
Traditionally, vehicles were tested in wind tunnels like this one, in which air is passed over a model of the vehicle and smoke trails are used to show how the air will move around the car. But because Bloodhound is going to be travelling so much faster, they've had to resort to using a supercomputer, some 200 times more powerful than a desktop PC, to work out how the air will flow round the car.
At the heart of computational fluid dynamics, or CFD as we refer to it, is essentially solving equations. So we will build up the set of equations that describe aerodynamics, and then we'll solve them. Essentially, they're a set of simultaneous equations, just like the simultaneous equations that will be solved in school, but we need a big supercomputer to solve them because they're quite complicated. On the left-hand side here, we're looking at the pressure distribution on the underside of the vehicle. So purple is high pressure, red is low pressure, and what we're always trying to do is minimise the amount of high pressure on the underneath of the vehicle because that results in lift on the car. On the right-hand side, we're actually looking at the pressure distribution over the desert itself. As well as being concerned about what the pressure is doing to the car, we're also interested in what the pressure is doing to the desert, because we don't want to damage the surface in such a way that the front wheels will degrade the surface so that the rear wheels have no solid surface to run on.
The Bloodhound team are using the same software to examine the airflow round the car as was used to help design the Airbus A380, the world's largest passenger aircraft.
The A380 is a very important aircraft in many ways because it was one of the first civil airliners that was designed solely using CFD technology. Up until the A380, most aircraft were designed using a combination of computational modelling and wind tunnel modelling. But the Airbus A380 was at the point in time where we had started putting more confidence in CFD modelling than wind tunnel modelling. The A380 aircraft is an incredible aircraft. It is huge. If you ever see it, it's hard to believe that it would ever actually take off. And of course, the team that designed that aircraft used CFD modelling to give them the confidence that that aircraft would fly, which of course now gives us the confidence that we've used the same techniques to design Bloodhound. So it gives us the confidence that what we've done is design a safe car that will get to 1,000 miles per hour.
The computer calculations have already forced the Bloodhound team to rethink their design at least once.
So this is the first design of the Bloodhound supersonic car, and lots of the big changes that we've made to the design of the car are focused at the back end here. In this configuration, the rocket is positioned on the top of the car, and it's actually generating an awful lot of thrust, 12 tons of thrust, which is more than the jet engine. So a combination of having the rocket positioned up here and also the strong shock waves that would be generated from the wheels in this configuration would have generated an awful lot of lift at the back end of the car, which at about 800, 850 miles an hour would have lifted the whole back end of the car up, firing the nose down into the ground. And you can imagine this travelling 850 miles an hour across the desert, flipping up like that would have been a catastrophic disaster. So a lot of the work that I've been doing has been identifying those problems. If it wasn't for the computational modelling, we may have tried running a car like this, which, of course, would have been potentially very dangerous.
So now the jet engine sits on top of the rocket. This graph shows Andy's speed against time. When he starts up the jet engine, he begins to accelerate. His speed increases fairly gently, about half a g. When he cuts in the reheat on the jet engine, the acceleration increases to 1 g. You can see that the gradient of the graph has increased. After 25 seconds, Andy fires the rocket. This is the steepest section of the graph, which shows he's reached maximum acceleration of 2.2 g. As his speed heads towards 1,000 miles per hour, the drag forces are increasing and reducing the total net force pushing forwards. So although he is still accelerating towards 1,000 miles per hour, his acceleration has now gone down to 1.5 g. After 42 seconds, SSC enters the measured mile. At this point, Andy is going at just over 1,000 miles per hour. The drag forces are so great that they balance the driving forces. The car is going at its terminal velocity. As soon as Andy cuts the engine, the drag forces are left on their own. They cause the car to decelerate enormously, about -3 g. Andy then deploys a 3-stage parachute to slow the car down further. The aim is to get the car to stop the same distance the other side of the measured mile, because they have to make another run going back the other way, and they don't want to have to move the car too far. The distance is shown by the area under the speed time graph. You can see that the area on the right is the same as the area on the left. It's up to the team back at Bloodhound headquarters in Bristol to work out how to actually fit all the bits of the car together. Once again, they're relying on a computer.
So as a project as a whole, we've got some massive challenges around fitting the jet engine and the rocket and all these fuel tanks and other systems into the structure, and into a structure that's going to be able to travel up to 1,000 miles an hour and then back down again, with all of the pressures and the forces that will be subjected not just to Andy, but also to the structure and all of those components within that structure. So it's a little bit like when you go around a roundabout quite quickly, and sometimes if there's several of you sat in the back of the car, you'll find yourself going over to one side and maybe your brother or your sister squashing you against the door. And it's the same for the fluids within the engine. The fact they get pushed to one side of the engine or they get pushed to the front of the engine. And the engine needs to have the fluid in the right place to work properly. That's a real challenge.
There are many thousands more hours of work to be done before the car finally attempts to make it into the record books. For now, the closest Andy Green can get to experiencing driving at 1,000 miles per hour is back in the cockpit of his personal plane.
No one has ever done this before. No one has solved those problems. We are coming up with new science. And that starts with the basic maths in terms of the manipulating the numbers, in terms of the basic chemistry of the reaction in the rocket, in terms of the basic physics of what actually happens at a wheel rim. We're taking basic science and taking it to its absolute limit at 1,000 miles an hour. As far as I'm concerned, science just doesn't get much more exciting than this.